I'm Stan Moore from Sandia National Labs in Albuquerque, New Mexico. I've been at Sandia for about 10 years. I'm the main developer of the Kokkos package in LAMMPS, which uses the Kokkos library. I have previous expertise in long-range electrostatics methods, and I did a PhD in chemical engineering, and my dissertation was on molecular dynamics and predicting chemical potential. Okay, so what are molecular dynamics? So classical molecular dynamics model behavior of atoms using Newton's laws of motion, but neglecting electrons. So we have the atom positions, we calculate some forces based on an empirical potential, typically, that can allow us to update the velocities, and then we get new positions. And typically we'll use a spherical cutoff, which gives very good linear scaling, and so we can simulate billions or even trillions of atoms on a large supercomputer. So you can see here, this is our LAMMPS logo. Particles bounce around, and then the trajectories are reversed, and we get back to the LAMMPS logo. Okay, so what is LAMMPS? LAMMPS is open source molecular dynamics code. It's open source, lamps.org, also on GitHub. So it not only can model atoms, but also it's a general particle simulator of many length and time scales, so we can look at actually model electrons classically, atoms, coarse-grained, and even coupling to continuum. It uses domain decomposition for parallelism, and we can do energy minimization, etc. It's enhanced through Kokkos as well as native CUDA for GPUs, as well as OpenMP, and it can be coupled to other codes as well. Okay, so finally, what is Kokkos? So Kokkos is a performance portability library. It was originally developed at Sandia, but it's now used by many other codes. It's also open source on GitHub, and what it really allows us to do is write our code once in C++, and then we can map our code onto different backend languages, such as CUDA, HIP, SYCL, etc. So that's this parallel dispatch. The second part of Kokkos are these Kokkos views, which are arrays that can be optimized for a specific hardware at compile time. So with just compiling with a different layout, we can optimize for GPUs or CPUs. So this would be like a Fortran style column major versus C style row major. It's used on top of MPI, so we're doing multi-threading on top of MPI, and as I said before, it's on GitHub. Okay, so we took this Kokkos package, or this Kokkos library, and we implemented it into LAMMPS as the Kokkos all caps package. There are actually other accelerator packages in LAMMPS. So there's just the regular C++ version with no acceleration, and then we have a few others. The names are slightly out of date. This is the OpenMP package. It's native OpenMP threading. The Intel package is also OpenMP threading, but it uses very advanced hardware intrinsics. It's very fast, but it's very complex code. Then there's the GPU package in LAMMPS. This is native CUDA as well as OpenCL support. And the difference between the GPU package and the Kokkos package is mainly the GPU package only accelerates the pair style, so the force computation, as well as a few other kernels. Everything else runs on the host CPU, and so you need to parallelize that using multiple MPI rings per GPU. The Kokkos package tries to be GPU resident, meaning everything runs on the device, including the time integrator, any diagnostics, any kernel that is heavy tries to run on the GPU. And as I said before, Kokkos supports different backends such as CUDA, HIP, SYCL, and even OpenMP multi-threading. So when I say Kokkos, you can really, this is really applicable to CUDA as well. Okay, so there's several different benchmarks in LAMMPS. We call them the standard benchmarks. So the most famous is the Lennard-Jones benchmark. Today I'll be talking about the chain benchmark. So this is a polymer melt of 100 atom chains. It's a simple bead spring model. So you have Leonard Jones as the bead, and then a Feeney bond, which is similar to like a harmonic bond, as the spring. It uses only repulsive pairwise interactions. So this is the Leonard Jones potential, you have this minimum energy well, and then an attractive tail and a repulsive wall. We're truncating it at a very short cutoff so that we only get the repulsive part. Typically, we'll truncate out to 2.5 sigma, and then we'll get the attractive part as well. And so this is a very lightweight benchmark. There's not a lot of compute. It's mostly memory operations, reading the coefficients, and then we also have a Langevin thermostat on top of the velocity relay time integrator. Okay, so how do we go about optimizing this benchmark? Well, I'm using several different profiling tools. In this talk, I'm mostly showing simple tools such as Kokkos tools, which is a part of the Kokkos performance portability ecosystem, as well as GNU gprof and this NVIDIA Insight systems on the command line. So in practice, I still use NVProf a lot just for simple profiling. It's now deprecated, but the functionality can be duplicated using this insys nvprof command. So I'm not claiming that these are the best tools. This is just what I'm showing. There are other more advanced tools, such as that have nice GUIs like NVIDIA Insight Systems, AMD Omnitrace, vTune, Tau, and HPC Toolkit that could be useful, but I'm not going to cover those in my talk. And then I wanted to make a distinction between Insight Systems versus Insight Compute. So systems is really for profiling the whole application, looking at all the kernels, whereas Insight Compute and the corresponding AMD Omnitrace are useful for diving into a single kernel, looking at the limiters, and trying to optimize a single kernel. And Evan Weinberg in the next talk will actually talk a little bit more about these Insight tools. Okay, so all of my benchmarking is done on the Argonne ALCF Polaris. It's a A100 GPU. To do my baseline, I'm only using 1 MPI per GPU. I'm using the LAMMPS stable version, the latest stable, using all default Kokkos package options. I'll mention that all of the pair and fixed styles are already ported to Kokkos. So the Leonard Jones pairwise interactions, the force kernel is ported. The Langevin and velocity relay time integrators are ported. The neighborless build is ported. I'm running for 1,000 time steps, and I'm only doing thermal output on the first and last time step. I'm using 2 million atoms on a single A100 GPU. The first thing I'll say is step 0 is to use CUDA-aware MPI on Polaris. And you just simply have to export environment variable. If you don't do this, you will get very slow performance. And then this is my MPI run command. I'm just running the benchmark. This sets the size of the problem to be 2 million atoms. And then these commands turn on Kokkos. So I'm saying Kokkos on with 1 GPU, and then this is the suffix command. So my baseline performance is 7.3 time steps per second. So higher is better. So I would call this a decent baseline, but also a little naive because there's things that we can do to tune performance. So if we look at the timing breakdown in the LAMMPS log file, which is output after every run, we can see that we have a very high amount in COM. And so that's very troubling. So something is not running well. There should be almost no time in communication because this is only a single GPU. We don't have MPI. There's no message passing going on. Okay, so another tool we can use is one of my favorites, the Kokkos tool space-time stack. So this is basically a simple tool that shows where your time as well as memory is spent if you're running a Kokkos code. And the nice thing about this tool is that it's MPI aware. And it's very simple to use. You just set an environment variable, so you compile the tool. It's a simple makefile, and then you just export this environment variable, and then you'll get the tool output. This shows that the largest GPU kernel is the neighbor build, the neighborless build, but it's not like really high, and so it's not matching what we're seeing with the LAMMPS log file. So there must be some significant host computation that's not captured by the tool, by the GPU profiler. So if we use the CPU profiler, gprof, it's very simple. We just compile a new executable with the -pg flag, and then rerun, and then we use this gprof on the executable. And this shows that we have an enormous amount of time in the atom map. And so what is the atom map? So the atom map is a map basically for global to local IDs. We need that to build the bond topology list for our bonded calculations. And this code is not yet ported to Kokkos, so it's running on the host CPU. It's built every time we reneighbor, and so that's about 3.5 time steps on average. And there are actually two styles of atom map. One is a simple array, and another is a hash. And the chain input by default hard codes this hash atom map style. Hash is also the default for more than 1 million atoms. If you try to use the array style with 1 billion atoms, then you're going to run out of memory. It's not going to work. But because we're only running on a single GPU, we can try using this array style, and it turns out that gives us almost 16x speed up. The reason is that host insertion for Kokkos unordered map, when you're running with CUDA but trying to use it on the host CPU, it's not optimized to remove all of the thread safety, like the atomics or the compare and swap. And so it's extremely slow. So just changing to this array style where we're just filling up an array instead of using this unordered map gives us a very large speed up. Okay, so what else can we do? We've got a large speed up, but is there more? Well, LAMMPS builds neighbor lists, basically the list of atoms for this central atom inside a spherical cutoff. So this is 2D, but in reality it'd be 3D. There's also what's called a neighbor skin, which is an extra distance beyond the cutoff that allows our neighbor list to be built less often. And so, as I showed previously, the neighbor list is expensive, and also when we build the neighbor list, we have to build this atom map on the host CPU. So if we could build less often, that would be good. And so we can optimize this parameter. So we're going to keep this array style for now, but increase the neighbor skin distance. And this will, like I said, allow us to build the neighbor list and the atom map less often. However, if we increase the skin distance, then every time we compute the force, we have to loop over more atoms. So there's a trade-off. We can't make it too large. There's definitely an optimal value. And so by optimizing this, value, I found that value of a little over 2x larger than the CPU default was optimal. So that gave not quite a 2x speed up, just increasing this neighbor skin size as well. Okay, so what else? In LAMMPS, there are a full neighbor list and a half neighbor list. So for a full neighbor list, each pair is stored twice. For a simple pairwise potential like Lennard-Jones, we can actually use a half neighbor list and only store each pair once. Typically, the full neighbor list is faster on GPUs because it doesn't require atomics, but we have to do twice as many operations to build the neighbor list. So if you use a half neighbor list, it requires atomics, but the A100 GPU has fast hardware atomics for double precision, and so it's really not an issue. And then one more option is the Newton flag. So because of Newton's third law, these pairwise interactions are equal and opposite on the two different atoms. And so either both processors can compute the interaction and not communicate the force, or you can set this Newton flag to on, and it will save computation but increase communication. And this depends on problem size and a few different factors, but typically Newton off is better for GPUs. However, if we try to optimize these parameters, we can try a half neighbor list. So the default is a full neighbor list with Newton off, because that's typically the best. But if we try a half neighbor list with Newton off and on, we see that our previous value was 198. If we use a half neighbor list, then we get a speed up. And then if we use both a half neighbor list and Newton on, then we get almost 1.2x speed up. And the reason is that this half neighbor list reduces the time spent building the neighbor list, since we're looking over fewer neighbors. Okay, another option in LAMMPS is atom sorting, or also known as reordering. So LAMMPS will periodically bin up the atoms in a 3D position and then reorder by swapping around the atoms all of the atom arrays. So position, velocity, etc. And the reason is that this can improve data locality and cache excess patterns. The default is at every 1,000 time steps. This is also currently done on the host CPU. And so we can optimize the bin size for binning this 3D position for atom sorting. If we do that, then we could get a very small speed up. So this is just increasing the bin size by a little bit over 2x. Okay, finally, CUDA MPS. So we know that we have some kernels running on the host CPU. And one way to parallelize that, so they're running in serial. One way to parallelize that is to use more than one MPI rank per GPU. The disadvantage is that this will also strong scale our kernels running on the GPU. However, we have 2 million atoms. That's a lot of work. And so we should be able to run more than one MPI rank to speed up this host calculation. And when running on NVIDIA GPUs, you absolutely 100% must use CUDA MPS, or you will greatly suffer in performance. This is a daemon that runs in the background. It launches the kernels from all ranks into the same CUDA context. Here's a link for more info. And so if we enable MPS, we just start the daemon in the background, and then we run on 8 instead of 1 MPI ranks. Then we get a small speed up, almost 5%, because we're parallelizing the host computation. Okay, so we're really out of tuning parameters so far, but without any changes to the code, just small tweaks to the input as well as the Kokkos package options gave us a 35x speed up from the baseline. The baseline used all default values and didn't modify the input script. But remember, we're still using this array style atom map. This is not going to scale to billions of atoms. We'll run out of memory. If we change to the hash style atom map, but using the previous tune values, then we drop to 90 time steps per second. The previous value was 253. So really, we're out of tuning options. Now let's go and let's modify the code to see if we can improve performance. So here's an updated profile. You can see that previously we had a very large time spent in COM. That's now gone. That was the atom map build. So we've changed to array style. We've parallelized it using CUDA MPS, etc. Here's the GPU profile with the Kokkos tools. You can see that the pairwise calculation is the most expensive kernel, and then the bond calculation, and then the neighbor list build. So we've greatly reduced this time spent in building the neighbor list. And here's the CPU profile. So we can see that we still have, this is the atom sorting on the host CPU, and this is the atom map. So we need to take care of this by porting these kernels to Kokkos. Okay, so the first thing that I did is I updated the Kokkos version to 3.7.1. So I was previously using the latest stable, which used 3.6.1. And it turns out that Evan Weinberg from NVIDIA actually fixed an issue with the CUDA occupancy calculations, where it was giving us a non-optimal value. And this actually gave over 10% speed up for the change benchmark, just updating the Kokkos version, which was great. Okay, so here are a few suggestions on how to optimize GPU performance. The first thing is to saturate the GPU threads. You need enough work so that you can keep the GPU busy. We're running 2 million atoms per GPU. That was just a random number that I picked. That should be plenty of work for the GPU, so this isn't really relevant for this system size. If we were running only 1,000 or a few tens of thousands of atoms, then we may need to look more into exposing more work by trying to thread over neighbors, etc. The second suggestion is to avoid launch latency overhead for small systems. So basically fusing kernels, fusing data transfers. So we're going to experiment with this. Number 3, port all kernels of Kokkos. So we know that the atom map and the atom sorting are running on the host. We need to fix that. Keep all atom data in GPU memory. So we need to try to find if we have any data transfer between CPU and GPU. Porting these kernels to Kokkos will also help with that, because if we have anything running on the host CPU, we have to transfer all the data that's needed by that kernel to the host CPU, run our kernel, and then any data that was modified has to be pushed back up to the GPU, which has a lot of overhead. Another thing to watch out for is allocating memory. So we want to over-allocate our views and only grow if the size is exceeded, so we're going to check for this. Use caches efficiently, so looking at data layouts, etc. So one thing we could try is sorting the atom list more often to improve the data locality. And then Kokkos view initialization is on by default. We need to make sure that that's not a bottleneck as well. Okay, so how do we find, check for this? How do we do that? Well, one tool that we can use is the Kokkos kernel logger. So this shows every single kernel launch by Kokkos. It can be a little bit of information overload, but things to look for. So this is view initialization. So if you see any of these, especially, so one thing you need to make sure is that you're looking inside the LAMMPS run. So you get a lot of these at the beginning when you're just setting up the simulation, which is to be expected. But if inside the LAMMPS run, you're getting a lot of view initialization, you need to address that. The same for allocations. So if you're allocating memory during the run, then other than just occasionally, if your system size is growing, you need to address that by over-allocating the views by a small amount. Another thing to look for is memory or data movement. So that would be a Kokkos deep copy. So if you're moving data from the host to the device or vice versa. And so really, you just need to find where you are in the relay run loop, and then find a specific kernel like the integrator, and then just start looking through all the kernels and look at try to find these overheads. And so I did that and removed some initialization. You can prevent initialization using this Kokkos variable. There's also a helper function in LAMMPS where you can reallocate memory, which will avoid initialization. I also removed some data transfer. It was on the size of the local atoms or in local. In the exchange communication, so I launched another few kernels using sort, but I got rid of this data transfer. And that gave about 5% speed up versus the previous performance. Okay, so we talked about kernel fusion. So there are times when you want to fuse kernels, and there are times when you want to split kernels. Fusing kernels is very good for small systems, lightweight potentials, reduces the kernel launch latency. It can also reduce the amount of global memory reads if you are in a loop. Instead of having to read the atom positions and the neighbor list data twice, you can just read it once if you fuse a kernel. However, if you have a large kernel, then actually splitting up the kernels can reduce register pressure. So we saw this with a very heavy benchmark, machine learning potential snap that Evan will talk about in the next talk. So for fission, you really need enough work so that you can hide or this launch latency is negligible. So fission is not going to work for chain. We need to do fusion. And so here's the basic MD Timestep. You have an initial integrate. This is the velocity relay or leapfrog. You have to do some MPI communication. Then we clear the forces, compute the forces, some more MPI communication if the Newton flag is on, the last part of the integrator, and then output. And then there's a huge caveat in LAMMPS. Computation of diagnostics, fixes, or compute can be scattered throughout this time step. But if you don't have any fixes, diagnostics in between number 1, and if you don't 1 and 6, and you don't have 7, then you can actually fuse these two kernels together. It's the same for 3 and 4 if you're using a full neighbor list. You can actually fuse the force zeroing with the computing the force. You just do that as the first operation. It will not work for a half neighbor list. So that's what we did. So I would say that LAMMPS' modular design is both a blessing and a curse. It's a blessing for adding new code, but it's a curse for GPU kernel launch latency. And so we can fuse the two kernels that I mentioned previously, with the caveat that you can't have any other kernel launches or function calls in between. So an example would be like an end of step fix in LAMMPS. So I added this fuse integrate kernel into fix NBE. This is the time integrator. And then there's logic that you have to add to check for these fixes to make sure it's safe to fuse. This gave a very small speed up, but I will mention that this is a large system. If I benchmarked a smaller system, then this would be a lot larger speed up. Okay, so as I said previously, atom sorting is running on the host CPU. We need to fix that. So I ported it to Kokkos, and then because I ported to Kokkos, it's a little bit less expensive. We can actually sort more often. There's a problem though. Currently, the way that it's done is that this Kokkos atom sort launches many CUDA kernels. There's one for every array, so like positions, velocities, etc. And so there's still some overhead. And so when I benchmarked it, I sorted more frequently, twice as, instead of 1,000 time steps, 500 time steps. I didn't see any speed up. So this is something I need to address in the future. I know that there are some overheads from sorting that I'll talk about on a future slide. Okay, so we talked about fusing kernels. You can also fuse data transfer. So an example would be sometimes you have different scalar flags. So if you have like an error or a warning, you need to transfer that from the GPU to the CPU so that you can throw an error. And so if you have multiple of these scalar views, you can actually fuse them into a 1D array. And then you can just use Kokkos subview to point to that 1D array so that you essentially have the same code as before. But then when you do your data transfer, you only have to do one launch of this data transfer instead of multiple. And so then you have a fused data copy. And then I also use a few temporary variables. So if you have repeated global memory loads, you can just use a temporary. So these are just small optimizations. Also found a place where there was some data transfer. But again, didn't really get much speed up because this is a large problem and these are little small optimizations. I think the speed up would be greater for a smaller problem. Okay, so we know that the atom map is a bottleneck. It's on the host still, so we need to port that. So what is the atom map doing? It's basically creating a map of global to local atom IDs. It also creates a list of all atoms with the same global ID. We call that a tag in LAMMPS. And so if we sort the local ID by the global ID, then we can build this atom map in parallel on the GPU, as well as this list of all atoms with the same global ID. And I will point out that because we are reducing the amount of work on the CPU, we also need to reduce the amount of MPI ranks with MPS from 8 to 2 for optimal performance. There's less work on the host CPU. using more than one MPI rank has some overhead, and so we don't need as many MPI ranks. And so when I went to profile this, the previous was 301 timesteps per second. I ported this to the GPU, and I actually got a performance regression. So performance went down. So why? Turns out that I broke my own rule. Avoid allocating memory every time step, over allocate views, and only grow if the sizes exceeded, don't shrink. So it turns out that allocating CUDA memory is expensive. You need to avoid this if possible. And the source was, when sorting to build this atom map, the parameters could change. So sometimes the number of atoms, the local atoms on a rank is different, and that changes the parameters for this bin sort. And so I was just reallocating this bin sort every time, and it turns out that internally, when the bin sort struct was reallocated, it reallocated several Kokkos views that were significant amount of memory. I used NVProf to track down the issue. It also shows up in kernel logger. So if I was more careful, I could have seen this in kernel logger. There was an issue with a few of my own views as well as the views inside bin sort. And so I was able to tweak the LAMMPS code so that most of these views over-allocated, and then I got a 6% speed up porting this atom map to Kokkos. And one thing that I wanted to mention is that this performance regression could have slipped through the cracks, could have gone unnoticed. But fortunately, I recently added scripts to measure performance on V100. I'm running 11 of the standard benchmarks in LAMMPS, including this chain benchmark. And it's automated through Jenkins. So with a push of a button, I can get feedback on, did I slow down the code? Did I speed up the code? There is some variance from run to run, so I'm averaging 8 replicas. This is important. Otherwise, you can get false positives or false negatives on the performance. I'm just comparing the latest develop branch, which I'm assuming is good, the good value, to my testing branch. And then if there's a performance loss of more than 3%, then it triggers a test failure. So I think this is really important. And it's also really satisfying. So when I make an optimization, I can see the performance gain on different benchmarks as I optimize LAMMPS. Okay, so here are the performance numbers so far. Our original naive baseline was only 7.3 timesteps per second. By tuning and changing some of the parameters and the input scripts with no changes to the source code, we got up to 253 timesteps per second. However, if you remember previously, this is the array atom style, which won't scale. So if we look at the latest performance with all the code optimizations and this array style, it's 321 timesteps per second. Because we ported this atom map to Kokkos, we can now use the hash version, and it gives a significant better performance. And this hash style will work at Exascale. We can run billions or trillions of atoms with the hash style. And so it's a little bit less than the array style, but we still get 315 timesteps per second. That's a 40x speed up over this naive baseline, and about 25% speed up from our best tune case. So that was the optimizations to the code over just tuning the parameters in the LAMMPS input script. I'll also mention that if you run this naive default no MPS with these code improvements, then it's a lot more forgiving. We're only leaving about half of the best performance on the table versus like over 30x for this really slow baseline. And so porting the atom map and a few other code improvements gave a large speed up just for the naive defaults. I compared performance to a CPU. This is an Intel Skylake, dual socket, 36 MPI ranks, and 2 OpenMP threads with the OpenMP package. And it's about 51 timesteps per second. So that was, I did, kind of the same tuning as here, and that was the best that I could see. And so we're significantly faster on the GPU A100 versus a full CPU node. I will also mention that tuning the bin size for the CPU gave a small performance improvement, and so perhaps the defaults in LAMMPS aren't optimal for either GPU or CPU, and we might want to look at modifying the default in the input script. And here's an updated profile. So here is the most expensive kernel according to the LAMMPS timing breakdown. That's the neighborless build. If we profile the GPU kernels, here is the neighborless build. And so for the GPU kernels, it's about the same for the forced computation, the Lennard-Jones pairwise interactions versus the neighborless build. In the LAMMPS output, the pairwise is about half of that, and so there might be a small discrepancy that I need to look into. Why is this higher? Is there something? I will say that I did profile the CPU, and there's nothing significant running on the CPU, so it's running fairly well. And then here's profiling using the first using the simple kernel timer. So this is another Kokkos tools. Reports that about 85% of the whole time is spent in Kokkos kernels. So there's maybe 15% overhead on the CPU. For insys NVProf, we can look at the different CUDA API statistics, and so you can see that the first three are basically device synchronize and other synchronizations, which is good. We want that to basically just be waiting for the kernels to finish. And we have very low overhead, and so CUDA free, CUDA memcopy, and CUDA malloc. So this all looks good. If these were high, like CUDA memcopy, that would mean that there's a lot of data movement, but we don't see that. So overall, everything looks pretty well optimized. There are still 2 views being reallocated every time step for sorting in the atom map. This unfortunately cannot be fixed in LAMMPS code. I have to go into the Kokkos code and submit a pull request on GitHub for Kokkos. So future work could include searching for other overheads that I may have missed. It would be good to use more advanced tools such as NVIDIA Insight Systems, which Evan's going to talk about a little bit next in the next talk. And then the corresponding AMD Omnitrace or other tools. And then if I can't find any other overheads like kernels diffuse, etc., then I would dive into the individual kernels, so like the Lennard-Jones, the bond calculations, the neighborless, etc. Look for limiters there using the vendor tools like Insight Compute versus systems for the whole application. And then look at roofline. How much room for improvement is there? Am I really close? Am I far? We've looked at Lennard-Jones. I think it's pretty well optimized. I really don't think that we're going to find much there, but maybe something in the other kernels like the bond calculations. Okay, so everything that I've showed for is for a single GPU. For multiple GPUs, we have to use more advanced communication patterns. So in LAMMPS, we have this domain decomposition. So each processor owns a subdomain of the total simulation box. And then we also have to create what's called a halo exchange or ghost atoms, ghost region, so that we can compute our pairwise interactions with the ghost values. And so this is necessary when you're running on more than one NPU rank per GPU. And so previously I fused many kernels so that the single GPU case is very well optimized. If we're using multiple GPUs, the Halo exchange requires 6 kernel launches to pack MPI buffers and another 6 to unpack MPI buffers. So that's a total of 12 kernel launches. So that's for the plus and minus X, Y, Z, so 6 directions. This method in LAMMPS prevents us from having to send many small MPI messages to up to 27 neighbors. So this would be like the subdomain corners. So this is 2D, so you can see that LAMMPS would just do 1, 2, 3, 4 passes instead of sending to the corners. For simple cases, I'll mention that you can skip the buffer unpack, so we're only launching 6 kernels instead of 12. But this is really just to say that if we're running on more than one MPI rank, or more than one GPU, then we have this overhead of a lot of kernel launches. This can hurt performance for small systems. And if you're running on more than one MPI rank, these kernels cannot be fused. They can at least all, if you're running on more than a few MPI ranks, then none of them can be fused. And so really, in summary, what I'm saying is that the LAMMPS Halo exchange is optimized to reduce MPI message latency, not CUDA kernel launch latency. So how can we get around this? Well, there's actually an ECP code called Cabana. It's a particle library, has several different algorithms for particles. The approach that they took is to pack a single buffer on the GPU, and then they send more, so like the 27 MPI messages instead of 6. So basically, you're trading MPI latency for CUDA kernel launch latency. So if we go back to this picture, they're sending to the corners. They only pack one buffer, but they're sending to the corners in 2E instead of packing 4 buffers and sending to the neighbors. And so this may be faster. This is research, so we're not sure, but could be faster for small systems, or if you're strong scaling, then that's like running a small system. And so this is something that we like to explore in the future. We could also add an option to the Kokkos package that you could optimize switching between the two for different system sizes, etc. Okay, so in conclusion, this really shows that even if your potential in LAMMPS is ported to Kokkos, even if you're running the best defaults that we have, you may not be getting the optimal performance. You may need to tune the parameters either in the input script or even the Kokkos package options for GPUs. You really need all kernels running on the GPU. So the main issue was that the Atom map was running on the host CPU. That was a bottleneck. And so once we ported that, we saw a speed up. Fusing kernels and data transfers can give speed up. We didn't really see it for our 2 million Atom system, but for small systems, this definitely gives speed up. CUDA malloc and view initialization are expensive. They need to be avoided when possible. So over allocate your views. Make sure you're not allocating memory every time step. Another thing that we learned is that this Kokkos unordered map insertion on the host CPU is very slow when you're running on GPUs. It has some issues with the thread safety that maybe we could address with the Kokkos developers. I will mention that the strategy for optimizing lightweight benchmarks like chain is different than when optimizing very expensive machine learning potentials like Snap. So this, I think, will be highlighted by the next talk by Evan. So I'll say that for the chain benchmark, many little things matter. So fusing, all these overheads we have to get rid of. We have to make sure that everything is running on the GPU. For Snap or a different expensive machine learning potential, basically nothing like this matters because it's so expensive. There's so many flops in the force kernel that's the only thing that matters. So I think you'll see that in the next talk. So with that, I'll thank you and take any questions.